Welcome to 5.2, the real zeros of polynomial functions and complex zeros. So here we're going to be breaking down our polynomials into our real numbers as well as our complex numbers. This is very similar to what we did at the very beginning, which was factoring polynomials by factoring. But in this case, we're going to solve, and we're going to solve using not only real numbers, but complex numbers. In slide 2, we go over a step-by-step of how to solve a polynomial equation. In this case, you can see that the equation is being set in the form of p of x is equal to 0, meaning that polynomial, whatever that polynomial might be, would be set to 0. We're going to go ahead and factor out that equation, and then we're going to use the zero product property in order to find the roots. If you can't use a zero product property, then you're going to use the rational zero theorem depending on the scenario that you're in. So if you go ahead and take a look at this example that we have at the very bottom, we first start off with 3x to the fourth plus 12x to the second. The first thing we want to do is set everything equal to 0. So we're going to bring over the 6x to the third. Once we have done that, because all of our coefficients are divisible by 3, we will divide our entire problem by 3 on both sides. When we do, we end up with x to the fourth minus 2x to the third plus 4x squared. We still have a common denominator, or a common factor, throughout all three terms, which is x to the second power. Notice we take out that greatest common factor, and now we have x to the second, parentheses x squared minus 2x plus 4. Once we are at this point, we are going to separate those two pieces, the greatest common factor and the factored polynomial equation, and we set it equal to 0. So x squared would give us 0, which means x is equal to 0, and that's where we get our first solution from. In the second scenario, or our second part, we have x squared minus 2x plus 4. In this case, because of the fact that this does not break down, we would go ahead and set it equal to 0. As we start moving over our terms, we will eventually get this part of our equation to give us the remaining part of 1 plus or minus I with the square root of 3. So let's go ahead. Let's take a look at our first equation. Now, as we are looking at our next problem on slide 3, the first thing that we need to do is find our P's and Q's. So in this case, our P and Q, P would be 2, Q would be 15. And what's going to happen is that we are going to find the factors of those numbers. So for 2, it would be 1 and 2. For Q being 15, it would be 1, 3, 5, and 15. So in order for us to find all of our possibilities, we are going to divide P by Q. And when we do that, we're going to find the positive and negative of each one. So what will occur is that we will look at our first number, and we'll do that in red. So our P is 1. So our first one would be a positive or negative of 1 over, and then we go to our first Q, which would be 1. From there, we would go on to our secondary P, which is going to be 2. So we would do plus or minus 2 over, notice our first Q, which is 1. Once we've done that, we can officially say that we've used 1 for all of our P's, which means we no longer have to use that from that point forward. So we continue going with plus or minus 1 over 3 plus or minus 2 over 3. And we keep going until we have used each one of our terms. So notice the next one would be plus or minus 1 over 5 plus or minus 2 over 5. Once again, we've used our 5, and we move on to the next q for our denominator. So plus or minus 1 over 15 plus or minus 2 over 15. These would be all of the possibilities that we have to break down that problem. Now, in this case, what will occur is we are taking a look at how we can go ahead and how we can break down and figure out our factors. The long method behind this would be that we would have to test out each one of the possibilities using our synthetic division and use the remainder theorem, which basically states that if we have a remainder other than 0, it is not a factor. So we'll go ahead, we'll try with positive 1 first and see what occurs. So with a positive 1, keep in mind the inside portion would be 15, 14, negative 3, and negative 2. We go ahead, work our numbers. In this case, this would be 15. This would be 15, because 1 times 15 gives us 15. This would be 29. 1 times 29 gives us 29. 26. Once we combine our like terms, 26, which would leave us with 24. Keep in mind, the fact that we are remaining with 24 as our remainder means that a positive 1 does not work. So we would go ahead and do the same equation with negative 1. Keep in mind, our possibility states positive or negative 1. So we go ahead, work our negative 1. 15, 14, minus 3, minus 2. Bring down the 15. This would be negative 15. Negative 1 and positive 1 is a positive 1. This would leave us with negative 2, positive 2. Keep in mind, we end up with a remainder of 0. We know that x equaling negative 1 would be a factor of this entire polynomial. So there are two things that will come from this. First, it's understanding that we have x equaling negative 1, and we know that our depressed equation would be the remaining factor. Our depressed equation are the coefficients that are on the left side of our synthetic division. So if we originally start with 15, negative 1, and negative 2, this would actually turn into 15x squared minus x minus 2. And since we already know that negative 1 does work, we would turn that into a factor as well. Remember, we are trying to get everything set equal to 0, which means we add negative 1 to both sides, or a positive 1 to both sides, by moving over the negative 1. And that would leave us with x plus 1 as our factor. We're going to go ahead and factor out that right side. So 15x squared minus x minus 2 will turn into a 5x minus 2 and a 3x plus 1. Our other factor of x plus 1 drops down. Keep in mind, all of these factors will be equal to 0 in order to determine what the value of each one would be. So in this case, x plus 1 is equal to 0. 5x minus 2 is equal to 0. 3x plus 1 is equal to 0. This means x is equal to negative 1. 5x is equal to 2, which means x is equal to 2 over 5. And 3x is equal to negative 1, which means x is equal to negative 1 over 3. So our final answers for this problem would be that x is equal to negative 1, 2/5, and negative 1/3. Now, keep in mind, as we found these answers, these three answers are a part of all of the possibilities. If we take a look at negative 1, notice negative 1 would be right here. Notice it says positive or negative 1 over 1. We are looking at the negative 1 side of it. 2/5 and a negative 1/3. So our answers are within the possibility, so we know that we did get the correct answers. Let's go ahead and take a look at slide 4. In slide 4, we go on to describe various ways in which we can double check that our answers are coming out of this problem. So it says that the rational zero theorem gives a list of possible rational zeros of a polynomial function. Equivocally, the theorem gives all the possible rational roots of a polynomial equation. Now, the list that we come up with are all of the possibilities, but not every single number in the list will be a zero of the function. And we know that because we have tried some of our numbers and ended up with a remainder. So the ones that end up with a remainder are not part of the zeros of that function. And we would have to do synthetic division until we find our first zero of the function. The one thing that can be guaranteed is that the zeros of that polynomial will appear somewhere on that list. We go on to slide 5. And in slide 5, we go ahead and show a breakdown of what is occurring. So keep in mind, here we start off with a list of possible rational zeros for our polynomial. First thing we do is we find our p's, we find our q's. Remember, our q is always our first coefficient. Our p is the last coefficient. So in this case, p is a negative 2, q is 15. We will always do p divided by q when we are solving for our possibilities. So as you can see, we find our factors. In this case, for the top number, it's going to be 1 and 2. For the bottom, it's going to be 1, 3, 5, 15. And we go matching one by one until, notice, positive 1, positive 1. Then we go on to our next one, 2 and 1. By doing that, we are creating our possible lists in positive and negative form. Once we are fully completed, we get our entire list, which would be here. Now, there are times where some of these numbers do overlap, and you might end up with a 1 over 1. You end up with a positive 2 over 1, and then you end up with a 2 over 2, which is equal to our 1 over 1, which will give us a positive or negative 1. And we continue on with the process in slide 6. Notice here, they go on to show you that you will do the synthetic division for each one in order to find the 0. Notice our positive 1 gives us a remainder of 24, which means this cannot work. Once we tried the negative 1, we ended up with a remainder of 0, which means that negative 1 is a factor of the problem. So as we rewrite the problem with the root solution of the negative 1, we move over that negative 1 to the left-hand side, which means x plus 1 is a factor. We go ahead, write our depressed equation. So this part, once again, is our depressed equation. And we go on to write it as a polynomial, as you can see here. Once we write out our depressed equation as a polynomial, you go ahead, you break that down into its factored form. Once that has occurred, you go ahead, set each one of your factors equal to 0, and solve. Notice in slide 7, we have 3 questions that we can go ahead and work on. What I would suggest, pause it, try to work on these 7, on slide 7 on your own, and try to come up with your answers individually. We're going to go over these together now, and you can double check your answers. So let's first begin with our first problem. Here we have our P and our Q. In this case, this would be 1 and 2 for Q. We have 1, 2, 3, and 6 for our P. We go ahead and set P over Q. This would give us a positive negative 1 over 1, positive negative 2 over 1, positive negative 3 over 1, positive negative 6 over 1. Now that we've gone ahead and we have solved for the 1 of our P, we're going to go ahead and we're going to work with the second digit of our Q, which is going to be 2. So we start over again as positive negative 1 over 2, positive negative 2 over 2, positive negative 3 over 2, positive negative 6 over 2. Now, in this case, we are going to go ahead and we are going to simplify these answers once again in order to get a better understanding of where we at. So we are looking at positive negative 1, positive negative 2, positive negative 3, positive negative 6, positive negative 1/2. Notice here, positive negative 2 over 2 would give us 1. We have seen that number before, so we do not have to retry it the same way. We end up with positive negative 3 over 2. And the last one would be a positive negative 3, which is also similar to the problems that we had before. Now, from here, we go on and choose a positive negative 1 to begin working with. Let's start off with negative 1. With negative 1, we'll start a synthetic problem. In this case, 2, 1, negative 7, negative 6, 2 drops down, negative 2, this would be negative 1, positive 1 would be negative 6, positive 6, we end up with a 0. In this case, we ended up with a perfect scenario in which our first problem, or our first number that we tried, is a factor. This will not always be the case, and what will oftentimes happen is you may have to try multiple of your problems or multiple of your possibilities in order to see whether or not it is a possibility. So we go on. We know that x is equal to negative 1. And we also know that as we move it over, this would be at x plus 1 as a factor. Our depressed equation here would be 2x squared minus x minus 6. We go ahead and we work the problem out. Now, in order to factor this, you can use one of multiple different methods. If you want to multiply the first and last, you can. Keep in mind, first and last would be 12. Find the factors of 12. 1 and 12, 2 and 6, 3 and 4. Since we are looking for a difference of 1, and we know it's a difference because we have a negative on the outside, 3 and 4 would be our best case scenario. So this would turn into 2x squared minus 4x plus 3x minus 6. This would turn into 2x on the outside. When we split our polynomial in half and we find the greatest common factor, it would be 2x. We are left with x minus 2. On the right side, we're going to do the same. We factor out a 3, and we're left with x minus 2. We know that this has worked because our two parentheses are the same. So our factors here would be x minus 2 and 2x plus 3. The last remaining factor that we bring down is x plus 1. We're going to go ahead, set each one of them equal to 0. And in this case, x is equal to negative 1, x is equal to 2, and x is equal to negative 3 over 2 as our final answer. Let's go ahead and take a look at our secondary question. 3x to the third plus 9x squared plus 4x plus 12. With this polynomial, the first thing that we're going to do is find our p and find our q. Finding those factors are going to be, for q, it's going to be 1 and 3. And for 12, it's going to be 1, 2, 3, 6, and 12. Once we've done that, we're going to find our possibilities, and we will have to list the possibilities out. So we go ahead and write our p divided by q. Keep in mind, this will always be a positive negative number. In this case, positive negative 1 over 1, positive negative 2 over 1, positive negative 3 over 1, positive negative 4 over 1, positive negative 6 over 1, and positive or negative 12 over 1. Once we've done all of the ones in our denominator, we can hop over to 3's, which means positive negative 1 over 3, positive negative 2 over 3, positive negative 3 over 3, positive negative 6 over 3, positive negative 12 over 3. Now, these are a large number of possibilities that we are going to run into. What I'm going to do is I'm going to show you a shortcut method to be able to find our factors of this problem. So once you start taking a look at your Inspire, you go ahead, you head to your main page. We're going to go over to our Scratchpad, and we're going to find the zeros of an equation. So we go ahead to Menu, Algebra, which is 3, Polytools, which is 3, and Find Roots of Polynomial. Now we have to go ahead and be able to see that we are taking a look at our highest degree being 3, so we will make that change, and we hit OK. We are then going to write the coefficients of each one of our terms. So 3, positive 9, positive 4, and positive 12. We go ahead and select OK. And once we've done that, we verify that our equation looks and matches as the question that we were working on, and we hit Enter. In this case, we are seeing that the only polynomial or possibility that functions with this would be a negative 3. Now, even though negative 3 is the only option that's truly being given to us, we also have to keep in mind that we were looking at real numbers. So let's go ahead, let's take a look at our options once again. We can still perform our first step, which is to go ahead and do the synthetic division using negative 3. So we go ahead, we do negative 3 on the outside, and do the synthetic division for 3, 9, 4, and 12. Keep in mind, as that number on the outside finishes, that would be our remainder. Our 3 drops down. 3 times negative 3 is a negative 9. That would be 0. Times negative 3 would be 0, 4, negative 12, and 0. So in this case, it is accurate. Yes, negative 3 is a factor. So we know that x is equal to negative 3, and our first factor would be x plus 3. Our depressed equation in this case would be x squared plus 4. Now, even though we do have our depressed equation, we have to ask ourselves, can this be factorable? X squared plus 4 is not factorable, but we have to keep in mind that we do work with complex and real numbers. Now, this answer that we found as far as our first factor would be negative 3. That is a real solution. We can still work with the complex. So we're going to go ahead and we're going to set x squared plus 4 equal to 0, which means x squared is equal to negative 4. We get the square root of each side, which would leave us with x is equal to the positive negative of 2. Actually, let's split it up first. Negative 1 times 4. Our 4 is going to break down into x equaling a positive or negative. Square root of 4 would be 2, and the square root of a negative 1 would be I. So our two solutions that are coming out of this would be that x plus 3 is equal to 0, which means x is equal to negative 3. We had proven that before. Now, in this case, with x squared plus 4, we know that x would also be equal to positive 2i and negative 2i. We can verify that we have the proper answers for this problem because we do have 3 answers here, and our exponent is to the 3rd power. Now let's go ahead and look at other options that we have within our calculator. As we go to Menu, 3, Polytools, we have the ability to find complex roots of polynomials. We can still go through R1 and find polynomials, or find roots of polynomials, but instead of, rather than selecting real, we can select complex. We go ahead and hit OK, and the same process can occur once again. We would hit 3, 9, 4, and 12. We select OK, and in this case, we are looking at, once again, the same equation, and we hit enter. Now, the only issue with this would be that we are looking at a decimal rather than the actual value as a positive or negative 2i. What I would highly suggest, go ahead, keep this as our answer of positive or negative 2i in order to make this as easy for you as possible. Let's go ahead and take a look at our last problem. Here we have f of x is equal to 3x to the 3rd plus 11x squared plus 5x minus 3. Now, first thing to do would be find our p's and q's. P would be in the back, q is in the front. Notice our q is 1 and 3. Our p is 1 and 3. P divided by q would be equal to positive negative 1 over 1, positive negative 3 over 1. We then go on to our next number, which would be q being 3, positive negative 1 over 3, positive negative 3 over 3. So we go ahead and we can use this method once again. We go ahead into Menu, Algebra, Polytools, and find roots of polynomial. Our largest degree is 3, and we're going to look for any real roots. Go ahead, hit OK. As we do that, we insert our coefficients, 3, 11, 5, and negative 3, and hit OK. Make sure that your polynomial that's on your calculator does match up with the one given. You hit enter, and notice in this case, we actually came up with 3 answers. The main reason for that is we have the ability to get 3 real numbers, or we could end up with 1 real number, and we have 2 possible complex. It depends on the question. So it's always great to be able to understand what type of answers we could possibly see as solutions to a question. In this type of scenario, you can go ahead and select one of your 3 answers that you're being given, keep in mind we can always go ahead and even write it down as far as our answers: -3, -1, and a 1/3. -3, -1, and 1/3. You're going to choose one of your numbers to go ahead and do synthetic division with. In this case, let's go ahead and choose -1. So our numbers here would be 3, 11, 5, and -3. Bring down our 3. This would give us -3, 8, -8, -3, +3, which would leave us with 0. So this goes on to agree or confirm that -1 is a factor of this polynomial. We go ahead and write that x is equal to -1, which truly means that our factor is going to be x plus 1. Remember, what we're doing here is just moving over that -1 to the left-hand side. In order to do that, you have to add 1 to both sides. We go ahead and write our depressed equation, which in this case would be 3x squared plus 8x minus 3. As we go ahead and factor this out, remember you have multiple ways of being able to solve this. This problem will be factorable, and we know that because we have 3 real answers, real number answers, as the solutions that we initially got. We can factor this out in one of a couple different ways. Keep in mind, 3 times 3 will give us 9. Our different factors that make up 9 would be 1 and 9, 3 and 3. Keep in mind, the only one that's going to give us a possibility of reaching 8 would be 9 and 1. This would be 3x squared plus 9x minus x, or minus a 1x, minus 3. Find the greatest common factor for the left-hand side. 3x, and you are left with x plus 3. Find the greatest common factor for the right-hand side, which would be -1, and you're left with x plus 3. The entire goal is to make sure that you keep that right side and left side parentheses matching. Here we have x plus 3 as one parentheses and 3x minus 1 being the other. We drop down the x plus 1 as our last factor. Keep in mind we are setting each one of these equal to 0. Once we go ahead and set each one of these equations to be equal to 0, we are going to solve for x. So let's first start with our x plus 1. We already know that x plus 1 equals 0, which means x is equal to -1. We can repeat the same process for x plus 3 is equal to 0, which means x is equal to -3. 3x would be equal to 1, which means x is equal to 1 over 3. Once we've done that, notice we can confirm with the answers that we had previously that we had written down: -3, -1, and 1/3. Our answers do match up, and our answers are correct as far as the solutions for this problem. We can double check that we have the correct number of answers Our degree here is 3, which means we would have 3 answers. Let's go ahead and take a look at slide 8. In slide 8, we begin with the conjugate root theorem. So in this slide, we begin by going over if a plus bi is a root of a polynomial equation, then the non-real complex number of a minus bi is also a root. So keep in mind, this would be the conjugate. The conjugate is whenever you switch out the middle sign for a positive with a negative, or switching out a negative with a positive. So ultimately, you will end up with a pair of conjugate answers. Now, the same way that it works with bi, right, using I as our number, you can also work the exact same way with a square root. If we take a look at the second line, it says if a plus the square root of b is an irrational root, then a minus the square root of b is also a root. Let's go ahead and take a look at slide 9. In slide 9, we go over a table of possible answers for the type of degree and root that you would see within a polynomial. One thing to realize is that your degree and the number of roots that you have are equal. The type of roots that you would end up with can change depending on the number. So if you have a degree of 1 or an exponent of 1, you would end up with 1 root, and that would be a real root. If you have something to the square power, to the second power, you would have 2 answers as your roots. It could be 2 real roots, meaning positive or negative integer, 0 or some form of fraction or decimal, or 2 complex roots, meaning square roots, or working with I. With 3, notice, degree matches the number of answers or the number of roots. You could end up with 3 real roots, just as we did in our previous slide, in slide 7, or 1 real root and 2 complex. Something to notice is that you will always have your complex roots occur in pairs. So from our degree of 2 all the way up to 4, notice it could either be a pair of complex. For 3, it's a pair of complex plus a real, or 2 pairs of complex roots with, you could also have 2 real roots, or a mixture between 2 real roots and 2 complex roots. Let's go ahead and take a look at slide 10. It states a polynomial function with a degree of 5 has 4, 2 plus 3i, and 5i as its zeros. What are the other zeros? The first thing to understand is that when they're telling us the degree, they're telling us that there are 5 answers. Notice 4 is a real number. The other 2 plus 3i and 5i, are both complex, which means we need to take a look at the conjugate. This would mean that 2 plus 3i would also have a pair, which would be 2 minus 3i, and we would have 5i, which would be a negative 5i. Those would be our 2 answers, because notice they're asking for what are the other zeros. So they're not asking for you to list all 5. They're just looking for the missing 2 answers or roots for this problem. Try to work on the bottom one on your own. Now, as we take a look at this problem, it says a polynomial function of degree 4 has 2 with a multiplicity 0, with a 0 multiplicity of 2, and 2 minus I as its zeros. So let's first understand what is being said here. There are 4 answers because the degree is 4. And it's stating that it has 2 answers with a 0 multiplicity of 2, meaning that our answer of x equals 2 will occur twice. And it also has a 2 minus I as a solution. Keep in mind, this is a complex root, which means 2 plus I would also be an answer. So as we take a look at all of our possible zeros, it would be 2, 2, x equals 2 minus I, and x equaling 2 plus I would be the zeros for this problem. In slide 11, we are seeing the same problem that we saw before, but the difference here is what is the function. So we're no longer looking for the zeros or what x is equaling. We are now looking at what is the original polynomial that we started off with. So from our answers, what we are going to do is that we are going to bring over the positive 2's into the left-hand side. So from x equals 2, we're going to subtract 2 from both sides. We have x minus 2 would equal 0. And this would be our factor, x minus 2. Keep in mind, because this occurs twice, you would do the same thing. X minus 2. When working with x equals 2I, 2 minus I, we're going to bring over the entire piece all together. So this would turn into x minus, parentheses, 2 minus I. And that would equal 0. Now, as we go ahead and distribute this, this would give us x minus 2 plus I. Let's take a look at our third root. Now in this case, or correction, to our fourth root, which in this case, we're going to have x equals 2 plus I. Keep in mind, we're going to bring this entire piece over. X is equal to, x is equal to 2 plus I. As we bring it over, it would be 2 plus I, and we subtract that from both sides. So x minus 2 plus I would be equal to 0. We go ahead and distribute the negative. X minus 2 minus I would be equal to 0, and that would be our factor. Now, when it comes to the left side and the right side, what will occur is that you will have 2 separate parts. You can either decide to work with the x minus 2, or you have the option of substituting it out and working with something simpler. It is completely up to you as far as how you would want to work this problem. I would generally suggest substitution just to make your life a little bit easier. In order for you to do this, you would have to have something in common on both of them, both of your factors, in order to substitute out. For example, in this case, I would go ahead and see that we have an x minus 2 on both factors. When that occurs, I would say x minus 2 is equal to, and you can choose a variable that it's going to get replaced with. So for example, if we say y, or choose a variable that maybe would stick out a little bit more so that you do not forget to replace it back in. So let's go with a. We would then say that our first factor would be a plus 1, or technically plus I, and we would have a minus I. Remember, here, what we're trying to do is find the function, which means we are going to have to multiply these two together. Because they are the same besides the middle sign, we are looking at a difference of squares. So this would leave you with a squared minus I squared. And this is where we can begin to plug in our different pieces. First piece that we can plug in is x minus 2 for a. So we would have x minus 2 squared. Keep in mind, do not fall for a common mistake, which is just to say this will give us x squared and minus 4, or positive 4. This is the same as saying x minus 2 times x minus 2, which would leave us with x squared minus 2x plus 4, or x squared minus 4x plus 4. And that would be the answer for the left side. X squared minus 4x plus 4. The right side is working with I. Now, certain things to keep in mind would be that anytime that we have I to the first power, that would be equal to 1. So I to the first power is I. Now, when we have I to the second power, this would be equal to negative 1. If we had I to the third power, this would be equal to negative 1 times I, which is a negative I. And when we have I to the fourth power, it would be similar to I squared getting multiplied against I squared. So what's negative 1 times negative 1? This would give us a positive 1. This table on the right-hand side is extremely helpful when working with I. Highly suggest that you learn this table because it will help you when solving for your answers. Here we have the remaining part of this problem is a minus I squared. Well, I squared is negative 1. A minus of a negative 1 would be the same as a plus 1. And we have the ability to combine our like terms, which would be x squared minus 4x plus 5. Keep in mind, this piece that we have solved for is only the right side of our 4 different roots. we did the complex side. We still have to solve for the left side, which would be multiplying our x minus 2 and x minus 2. This x minus 2 that we did earlier, keep in mind, was a part of this right-hand side when we were replacing a with our x minus 2 and squaring it. So this would be x minus 2 times x minus 2, which would be x squared minus 4x plus 4. This part gets dropped down as well. And would be the secondary part to our answer. Now, I'm not going to have you go even further than that, but it is important to multiply all of your terms as far as possible. Let's take a look at slide 12. In slide 12, it says a quartic polynomial, p of x, has rational coefficient if the square root of 2 and 1 plus I are roots of p of x. What are the other two roots? So the first thing would be to take a look at our roots. If we have the square root of 2, it would also be the negative square root of 2. And if we were looking at 1 plus I, the conjugate of it would be 1 minus I. So now that we have taken a look at our conjugates, we need to see if it matches with our degree. In this case, it's saying a quartic polynomial, which means to the fourth power. We do have our 4 answers here, which means our 4 solutions to this problem would be x is equal to the negative square root of 2, x would equal the square root of 2, x would equal 1 plus I, and x would equal 1 minus I. If we were to go ahead and multiply to find our function, first we bring over all of our terms to the left-hand side. So this would be x plus the square root of 2. And that would be equal to 0. X minus the square root of 2 is equal to 0. X minus 1 plus I is equal to 0. And x minus 1 minus I is equal to 0. By doing that, we would then have to go ahead and start finding the terms that we are going to multiply against each other. Now, before I had shown you a method of using substitution, but you also have the ability not to substitute in. In this case, when we are finding our function, we're going to multiply our terms, and that would give you x plus the square root of 2 times x minus the square root of 2 times. Now, keep in mind this next piece, we are going to go ahead and distribute that negative. So this would be an x minus 1 minus I. And we would also have x minus 1 plus I. We do see that our x minus 1 is found in both of our complex answers. As we go ahead, we multiply the left side. This is a difference of squares. So x plus the square root of 2 and x minus the square root of 2. This would leave us with x squared minus, now square root of 2 times the square root of 2 would leave us with the square root of 4. Square root of 4 would be 2. That would be our left side answer. Let's focus on the right side now. This is the same issue. It's a difference of squares. So we would go ahead, grab our first term, x minus 1, and that would be to the second power. Minus I times plus I would leave us with a minus I to the second power. Now, as we simplify this, keep in mind a negative or subtraction of I squared would be the same as the subtraction of I squared is equal to negative 1, which would be the same as a plus 1. We go ahead and take care of x minus 1 to the second power, which would leave us with x squared minus 2x plus 1. We combine our final solutions of x squared minus 2x plus 1 and the plus 1 from the I squared to give us our final solution of x squared minus 2x plus 2 times our left side answer, which was x squared minus 2. Notice I am not having you go further than this. Let's go ahead and take a look at slide 13. In slide 13, it says writing a polynomial function with rational coefficients so that p of x is equal to 0 and it has the given roots. Keep in mind, even though we do have negative 6, 3, and negative 5i, a negative 5i would mean that it would also have a positive 5i as an answer. We would go ahead, x is equal to negative 6, x is equal to 3, x is equal to negative 5i, x is equal to 5i. We bring it over into its factored form, which would be x plus 6, x minus 3, and x plus 5i, and x minus 5i. We multiply our factors on the left-hand side, which would leave us with x squared minus 3x plus 6x minus 18. And this simplifies to x squared plus 3x minus 18. On the right-hand side, because it is a difference of squares, x times x is x squared. Positive and negative would give us a negative. 5i times 5i would give us 25i to the second power. Keep in mind, I squared would be the same as a negative 1, which means x squared plus 25 would be our left side answer. final answer here would be x squared plus 3x minus 18 times x squared plus 25 as a final answer. Let's go ahead and take a look at slide 14. So it says finding the remaining complex zeros of the given polynomial function. Here we have x to the third plus 3x squared plus 25x plus 75. It is giving us a 0, which would be negative 5i. If that is initially given, keep in mind there is another 0 of a positive 5i. We have 2 of our answers, and that's going to be 5i and negative 5i. Once we do that, we go ahead, put them into factored form, and we're going to multiply the 2 of them. Keep in mind, once we do, because it's a difference of squares, our middle 2 terms cancel out, and you can see that here. We are left with x squared minus 25, I to the second power. I to the second power is negative 1. That would leave you with x squared plus 25. Now we have, remember, found 2 of our 3 answers. In order to find that third answer, we're going to go over to slide 15. And we would have to do long division using that x squared plus 25 with the entire polynomial that we had before. Remember, long division, the entire goal is to make sure that that x squared is matching up with our first term, which is x to the third. So how do we make x to the second power match to x to the third? We multiply by x. X times x squared gives us x to the third. X times 25 would give us a positive 25x. Keep in mind, once we put it in that position, we are going to subtract. So what we really see here is the subtraction of a x to the third minus a positive x to the third, which would cancel off. We drop down to 3x to the second power. 25x cancels with 25x, and we drop down to 75. We repeat the entire process once again. 3 times x squared would give us that 3x squared that dropped down. We're using a positive 3 because remember, we want 3x squared that has dropped down. When subtracted with a positive 3x squared would leave us with 0. In this case, we go ahead and we end up with our 3x squared subtracting. 3 times 25 is 75. 75 minus 75 would give us 0. This is extremely important because it helps us to determine if we are coming up with the correct answer. Considering how we know that the other 2 factors or answers that we had solved, which was negative 5i and positive 5i, are factors, by dividing by x squared plus 25, we should come up to a remainder of 0. If our last factor is x plus 3, we would have to set it equal to 0 and solve for our zeros, which is negative 3, negative 5i, which we had from the beginning, and a positive 5i. In slide 16, we go over the rational root theorem and the step-by-step of how to find our proper answers. If you have any questions, please feel free to ask at any point.